Hello, dear friends, and it is my pleasure to introduce our today's special expert. Arthur Viterito is a professor of geography at the College of Southern Maryland, and he has previously held position at the University of Pittsburgh and at George Washington University. Professor Viterito is a policy advisor with the Heartland Institute. Professor Viterito, welcome to our interview and thank you very much for finding time for us.
Well, thank you very much. It's a pleasure to be here with you. I'm technically a retired professor. I studied at the University of Denver, taught at, as you said, the University of Pittsburgh and George Washington University, finished out my career at the College of Southern Maryland, and was asked by a student a number of years ago if the number of earthquakes on the planet had been increasing. And I said, yeah, they have slightly, but I haven't looked at the data carefully. And when I looked at the data carefully, I started to see some things that intrigued me. And what intrigued me most was the fact that the number of earthquakes was starting to increase rapidly on the ocean floors. And I said, gee, this looks kind of interesting because it sort of coincides with a large jump in temperature that we saw in 1995. And at that point, I started to research what I call the mid-ocean seismic activity. And sure enough, it's correlated very, very well with global temperatures. And I'm now at a point where I think I have what I would consider to be an emerging hypothesis on this.
Yeah, thank you very much for your introduction. And I think we know that you prepared the presentation.
Okay, the title of the presentation is a mid-ocean geothermal flux as a driver of recent global warming. And as I said, it's an emerging hypothesis. And it's fairly complex, but in its simplest terms, I think it's easily grasped by most. Now, the Earth is warmed by about 0.5 degrees Celsius since the 1950s. And the prevailing theory is that this has been caused by the burning of fossil fuels, which have released carbon dioxide into the atmosphere. And carbon dioxide is a greenhouse gas. And now when we say greenhouse gas, that means it, quote unquote, traps heat. That is, carbon dioxide can absorb infrared radiation from the Earth, causing the atmosphere to warm. The other major greenhouse gas in the atmosphere is water vapor. And water vapor is considered to be the greater of the greenhouse gases. The amount of infrared radiation absorbed by water vapor is greater than CO2, plus CO2, plus water vapor is much, much more abundant. And the next slide will illustrate this. We can see here that water vapor constitutes 95% of the greenhouse gases in the atmosphere. Carbon dioxide, by contrast, is only 3.6%. So we can see that there's a huge difference in the sheer amount of these two gases. But we also see that the amount that's attributable to human activity is only 0.12%. The rest of this is naturally occurring. This is from the US Department of Energy. And we see here that there is a huge disparity between the two gases, that is water vapor and carbon dioxide. However, the greenhouse gas advocates have claimed that it is this human component that is causing Earth to warm. As another way of looking at this graphic shows that if we take the total atmospheric composition, our atmosphere is 78% nitrogen, it is 21% oxygen, 0.93% argon, which is an inert gas. CO2 is this very small part down here, and anthropogenic or human-generated CO2 is 1 part per 10,000 parts of the total atmospheric composition. And the alarmists are positing that this is the main driver of recent global warming. The numbers don't seem to add up. In fact, the carbon dioxide catastrophists have shown us that this is how much warming we should have expected from the CO2. That's the line here in red. The figure down here shows us how much we've actually had based on a number of different observations. And as you can see, the predictions are nowhere near what is observed. In other words, the predictions show the atmosphere to be far warmer than it actually is. So in 2016, I created a hypothesis that says that the mid-ocean spreading zones can activity in those mid-ocean spreading zones can cause a concomitant rise in global temperature. And the mechanism is detailed in this flow chart. That is, if we have more geothermal energy coming up from the ocean floor, this will in turn intensify what we call the thermohaline circulation, which I'll explain. We have some good diagrams to show what this is. What most people don't realize is that the ocean is the main store of heat on the planet. The oceans contain 1,000 times as much heat as the overlying atmosphere does. So if we can intensify what we call the thermohaline circulation, which we'll show you in a second here, that means more heat will be transported into the Arctic. More heat into the Arctic will reduce the amount of snow and ice. It'll simply melt, reducing what we call the albedo, or the reflectivity of sunlight in the Arctic. And both the increase in ocean heat transport and the reduction in Arctic albedo will increase Arctic temperatures. This is referred to as a feedback mechanism. And in the literature, they refer to what we call here the Arctic amplification. And we'll explain all these points as we move forward. First, let's look at this idea of greater geothermal flux. Geothermal, of course, is heat that emanates out from the mantle of the Earth. It's what we see in active volcanoes, geysers, hot springs. And we see that the vast majority of geothermal heat on the planet, again, most people don't realize this, has its origins at the ocean floor. And this diagram here by Davies and Davies shows in red where most of the geothermal heat for the planet is emanated. And we can see that it perfectly matches up with the parts of the Earth's crust that are splitting apart. These are what we call the mid-ocean spreading zones, okay? And if we look at the mid-ocean spreading zones, we see that high earthquake activity in these regions indicates high flow of geothermal heat in these regions. So for the purposes of this discussion, we're going to refer to what I call MOSIA, mid-ocean spreading zone seismic activity, because it's what we call a proxy indicator. We don't have actual measurements of how much heat is being given off, but we do have some a fundamental understanding of its magnitude. So as we say here, MOSIA is a good proxy for the amount of geothermal flux. To this purpose, I've cataloged the number of seismic or earthquake events in the 4 to 6 range of what's called the moment magnitude range. This is commonly referred to as the Richter scale. This is the paper, the initial paper that I wrote on the subject back in 2016. And to quote from the literature, we're going to have to get a little sciencey here, but we can work through this. Seafloor hydrothermal systems are known to respond to seismic and magmatic activity along mid-ocean ridges, often resulting in locally positive changes in hydrothermal discharge rate, temperature at the time of earthquake swarms. That is, as you have more earthquakes in these mid-ocean spreading zones, you will have a greater release of geothermal heat. And I've tracked this. I've looked at the seismic activity in these mid-ocean spreading zones. And here's the chart. We can see that the mid-ocean seismic zone, seismic activity remained fairly constant up until 1994. In 1995, it started to increase, and it jumped up to much higher levels throughout the remainder of the 90s, and it just remained there. The trend line, which is in black, shows that the trend has been upward. So we know that we have greater geothermal flux because we have a lot more earthquake activity down on the ocean floor. And what this will do is it intensifies what we call the thermohaline circulation. This is intuitively very easy to understand. Thermo refers to temperature and haline refers to salt. And when we're talking about the movement of water, you have to look at its temperature and you have to look at its salinity, because the temperature and the salinity determine the density of that water. So what we have here on the planet, the thermohaline circulation, also called the meridional overturning circulation, or MOC, is driven by these density differences of temperature and salinity. And the oceans circulate in this giant conveyor belt, and we call this deep convection. Now, what's important to note here is that we have distinct zones of water that upwells, that is, comes up from the bottom to the surface. This is very cold water, designated here in blue. And then we have warmer currents at the surface, which eventually sink. And we find that the major sinking point of what is called downwelling occurs here in the northern Atlantic Ocean. And this is a critical driver of the recent warming that we've seen. So we can say that by applying spatially constant or variable heat fluxes to ocean general circulation models, we find that ocean geothermal heat is a significant forcing that can weaken the stability of the water column. It warms the bottom water, and when you warm the bottom water, you strengthen the thermohaline circulation. This is a well-established fact in oceanography. And so what happens, and I'm going to come back to the previous slide, this conveyor belt, if you heat the bottom through geothermal heating, what is going to happen is that this conveyor belt is going to move faster. And the faster this moves, the more heat gets pushed up into the Arctic. This is a critical mechanism that we have to pay careful attention to.
Can I ask you a question while we are this topic?
Please.
Some scientists say that the Gulf Stream is slowing down, and some say it's changing the direction.
That's very interesting. There is that argument that the Gulf Stream is slowing down, but it has been shown, and I didn't include this in here, that the overall circulation of the ocean has increased. An article came out about 2 years ago. I would have to pull it up in a different file. But we do know that ocean circulation has increased remarkably. The slowing down of the Gulf Stream is really not well documented. We have a very short period of record of what are called Argo buoys, that one study shows that it has increased. Modeling studies have shown that it's decreased. So The observations show it has increased. The models, the theoretical models, show that it has decreased. So there is a discrepancy there. But as I said, it's the modeling studies that say it's showed down, but the observational studies show that it is actually increased somewhat. Also, we know that it pulses over time. It increases, then decreases, increases, decreases. And that's because geothermal heat release is highly variable. What I showed you on that first graph is the yearly geothermal seismic activity. If you look month by month, you see that it's much more variable. It's much more noisy, so to speak. Now, in a landmark study, it was shown that geothermal heating stimulates convective activity in the Southern Ocean, and geothermal heat fluxes intensify the maximum of the Atlantic meridional overturning circulation by about 10%, and that is significant. Now, just to give us a perspective, one study showed that the Gulf Stream transports as much heat into the North Atlantic that's the equivalent of 10,000 medium-sized nuclear power plants. So we're talking tremendous amounts of heat involved here. So this increased oceanic heat transport into the Arctic is documented in many ways. First, here's the branch of the thermohaline circulation that we want to look at. It is the North Atlantic branch, and this part of the conveyor belt is what we call the Atlantic Meridional Overturning Circulation, or AMOC. This is well described, and there's a tremendous amount of literature that talks about this. Here we can see that this is a very, very large area of what we call downwelling. The warm water at the surface, the Gulf Stream is, and then of course the North Atlantic Drift, there are many branches to this, will then start to subside and become part of the deep bottom water. So the more intense this AMOC, the more heat is brought into the Arctic. And here we can see a more detailed diagram of the Gulf Stream and how it splits off into a number of other regional currents. So again, a landmark study done by Majan, Zhang, and Delworth shows that an intensification of the Atlantic Meridional Overturning Circulation is associated with an increase in the upward surface long-wave sensible and latent heat fluxes from the ocean to the atmosphere, along with an increased downward shortwave flux, i.e. sunlight, into the ocean via the reduction in the surface albedo, which is the reflectivity over Labrador, Greenland, the Barents Sea, in the fall and peaking in the winter, and we'll come back to this. We have data to back this up. The increased net upward heat flux from the ocean open surface, as well as through the thinly covered ice, further increases the surface air temperature. This is well documented. This is a Journal of Climate Study, peer-reviewed, highly regarded. So if we look at the current state, so to speak, of the Atlantic, we are now in what is referred to as the positive phase of the AMO, which is the Atlantic Multidecadal Oscillation. And this is what the temperature field looks like. And you can see here the areas in red, primarily in the central and northern Atlantic, have been running much, much warmer than normal. And I'm going to show you how we got to this state. We arrived at this state starting in 1995. That is, these anomalously high temperatures, giving us what we call a positive AMO, has been around since 1995. And we're going to link these two together when we start looking at our circumstantial evidence. So in addition to directly transporting heat into the Arctic, we know that we're also able to now reduce snow and ice, which reduces the reflectivity of the surfaces in the Arctic. As we all know, snow and ice are highly reflective. This is why if you go skiing, you'll wear ski goggles to protect your eyes. Here we see a shot taken from the NASA Earth Observatory in 1979, a snapshot of the snow and ice cover in the Arctic. Here, of course, we can see here in the bottom right-hand corner of this first image, here's Alaska, here's Greenland, up here at the top of the image. And we can see the extent of snow and ice in 1979. Here we can see on a typical day, the extent in 2007. We can see that it's been greatly reduced. And this is very, very important because as you melt snow and ice, you produce what is referred to as a positive feedback. That is, if you cover an ocean surface with snow and ice, you're going to reflect about 90% of that sunlight right back out into space. Only 10% is going to be able to penetrate and warm the ocean underneath it. However, if you remove the snow and ice, if you look at the right-hand side of the diagram, we see that without water and ice, the ocean now absorbs 94% of the incoming radiation, only reflects 6% of it, and that serves to amplify or feedback and warm the water even further. Here we see an interesting image around the Arctic, and it also looks at the snow and the permafrost. And we can see here that in the areas in deep purple, we have had continuous reduction in snow and permafrost. And here we see in the lighter purples, we have less of an impact, but the area that is adjacent to and encircling the Arctic is, if you will, it has been under continuous loss of snow and ice since 1995. So we say here that, and again, going back to Marjan, they state that an intensification of the AMOC inhibits sea ice formation, leading to the largest decrease in sea ice concentrations. So these decreases in sea ice concentrations have been well documented, they've been noted in the literature, and we know that this kicks in, this enables this positive feedback. So the net effect of all this, the intensification of the greater geothermal flux, which intensifies the thermohaline circulation, which increases oceanic heat transport in the Arctic, which also reduces snow and ice, results in increased Arctic temperatures. And sure enough, the data clearly show that the latest warming, this is going back now to 1995, has been concentrated at the North Polar region. The tropics have warmed a modest amount, South Pole has warmed virtually nothing. But we can see this Arctic amplification has definitely kicked in. We're going to try to pull this together and see both direct and circumstantial evidence to support the hypothesis. And first, we're going to look at some direct evidence in the form of statistical inference. Somebody said to me, well, you have to have some mathematical proof of this. I said, well, we put together a regression model for this. Well, you need math. I said, last time I looked, statistics was math. Here again is the first diagram that we showed you of the mid-ocean seismic activity, which is the proxy for geothermal flux. We've taken the trend line out. The reason we start this at 1979 is because this is the first year that satellite temperature data became available on a global scale. I believe this is the most accurate, it's the most comprehensive database. It is the least contaminated by surface changes, and also it has complete geographic coverage. So we're getting readings over the southern Indian Ocean and Antarctica and the middle of the Pacific, as opposed to just urban areas in Canada and the US. So this is, I think, the best data set that we can work with. Now, if we put the two of them together, we see this. The mid-ocean spreading zone seismic activity plus global temperature is the bar graph in blue. Global temperatures are the curve in red. And we can see they kind of match up, but you almost have double vision. The peaks don't and the valleys don't quite line up. However, if we do a simple adjustment to the data, that is, we do a 2-year lag adjustment, we find that the temperatures lag the mid-ocean seismic activity by 2 years. We can see the peaks line up very, very nicely, and even the valleys line up very, very nicely. There's a little anomaly going on right here at the current time, which I'm describing in this paper I'm writing now. There was a weak El Nino that hit, which elevated the temperatures, but as you can see, they're coming back down now, in line with what the seismic activity would lead us to believe. If we make them both line graphs, and we match them up together with that 2-year lag, because it takes about 2 years for the temperature changes to start to work their way through the system and start to manifest themselves in warmer global temperatures. We see that these two curves match up very, very nicely. This is a very tight fit. We call this a goodness of fit. And the correlation coefficient on this is 0.72, which is statistically significant, very high. The mid-ocean seismic activity, which is our indicator of geothermal heat, is explaining 52% of the variation in global temperatures over the last 42 years. We're now going to present some circumstantial evidence, which is really quite stunning. And 1995 was a very, very important year because it was an inflection point in global temperatures. That is, the mid-ocean seismic activity and consequently geothermal release suddenly spiked up in 1995. And we see that a number of other geophysical phenomena also changed in 1995 because it's all connected. And here 1995 is designated with a green arrow. So first, if we look at our mid-ocean seismic zone, it's the spreading zone seismic activity, we see in 1995, after a relative period of quiescence with a few ups and downs, it starts to move up significantly higher in 95, and then it jumps up in 96 and 97. But 95 is the inflection point. This is when it sort of breaks the trend line, the flat trend line that was in the 70s and 80s. In fact, this is a period of time when all of the media were talking about global cooling, and that was the catastrophe of the day. But as you can see here, by 1995, the MOSA, or the mid-ocean spreading zone activity, starts to move higher. Now remember that AMO index we showed before? We also see in 1995 that the AMO, or the Atlantic Multidecadal Oscillator, which tracks North Atlantic temperatures, we see that also changed phase, or it flipped from what we're calling negative phase, that is cooler ocean temperatures in blue, and in 1995 it flipped to warmer ocean temperatures. Precisely the same year that all of the seismic activity in the oceans jumped up. Here we can throw in another variable. We identify the AMO warm phase back in the earlier part of the century, a cold phase, and then finally the warm phase. We see it again, lines up perfectly with 1995. In addition to that, the blue bars here show what we call the ACE, or the Accumulated Cyclonic Energy Index. It tells us how much energy is being released by cyclones in the North Atlantic. Here we see the North Atlantic Accumulated Cyclone Energy Index. That is, that index also jumped sharply in 1995. And you need high sea surface temperatures in order to generate hurricane activity. And we see that it perfectly coincides with when the AMO flipped from a cold phase to a warm phase. But again, 1995 was that demarcation point. Here we see Arctic temperatures. This is provided by the Danish Meteorological Institute. And we see here that in 1995, we started to see a sharp and significant increase in the spring and fall temperatures. Again, 1995 is designated here with the green arrow. We see that the spring temperatures, which are in green, and the fall temperatures, which are in red, showed a definite spike upward. and have continued upward ever since 1995. Lagging was the winter temperatures. These are in blue. They had about a 2 to 3 year lag behind that, but now we can see that they have now, that curve is now caught up, and that curve has gone much, much higher. Interestingly, the summer Arctic temperatures are flat. They don't change. Most of this is occurring in the fall, the spring, and the summer. Here we see the total ice area in the Arctic. And again, we see in 1995, designated by the green arrow, this is the year it gaps downward. Here we also see cloud cover in the Greenland sector. Again, in 1995, it gaps downward. The mechanism involved here is the fact that as temperatures start to increase in the Greenland sector, the atmosphere can hold more water vapor. In other words, less of the water vapor that evaporates from the surface will condense into clouds because the overlying atmosphere is warmer. So this will result in a reduction of cloud cover. And finally, here we take a look at what is called the subpolar gyre, which is a large circulating mass of water centered around Iceland. And we can see that the sea surface temperatures in the SPG jumped up starting in 1995. So we have this large concurrence of other geophysical phenomena perfectly matching up with the sudden surge in seismic activity in the mid-oceans. And this, of course, is a reflection of the higher geothermal heat coming out of the mid-oceans and an uptick in the intensity of the thermohaline circulation.
Wonderful. Thank you very much. Amazing presentation. So let's talk about the data a little bit, about which data, where we can take an honest one, and which one are you using in order to show us?
For the earthquake data, that is it's called the Iris Wilbur 3. It is an international consortium. The USGS is one of the participants. The Iris Wilbur 3 data set is a comprehensive global seismic network. It's been around since the early 70s, but it has morphed from the, I forget what the old name was. It was called the Worldwide Seismic Network, and now it's called the Global Seismic Network. And it's now an automated system. There is, it's an extensive database. I've captured over about 2 million pieces of data off of this. And I've boiled it down to looking at the data pieces that correspond with the mid-ocean spreading zones. Those are identified in the database. I have cataloged that, and I will be happy to share that with anybody who's interested in it.
Wonderful. Yes, we would be the guys who are very interested into this kind of data. And also, is it an open source? Anybody can look it up? Is it, or
Yes.
You have to be prepaid somehow?
No, it's open source. There are no paywalls.
Wonderful. Would you share the link as well, where we could go through this backward?
Yeah, it's Iris 3 international. It's an international consortium of seismic information.
Wonderful. Next question for you: what is causing the geothermal flux increase? Why? Like, I understand it's a driving factor into the warming of the ocean, which then drives the weather and climate change and everything else. Do you know the reason why it's so active these days?
If I knew that answer, I would be in Scandinavia collecting my Nobel Prize right now. That is an unknown. There are a number of theories out there. For example, one theory is that the what's called the shifting barycenter, or center of gravity between Earth, Sun, Jupiter, and Saturn, has shifted, and what it does is it causes the plates to flex. There's a stronger gravitational force on Earth's crust. There's another one that says, well, it all has to do with internal generation, and we see a pulsing effect of an exhaustion of internal energy to the system, and then it replenishes itself, sort of like the old faithful geyser. So there are competing theories on this, and nobody knows for sure. That's a great unknown.
Also, there is evidence that there is geothermal flux under Antarctica and
Yes.
also Greenland, which is causing the melting of the ice from the bottom up.
Yes. That is well documented. A researcher by the name of James Camus has done a lot of research on this. In fact, he has a book out called Plate Climatology Theory. And he explained this very nicely. He's documented these fluxes under the ice sheets. And we do know, and we do have very good data that shows that, yes, a lot of the ice melt from Antarctica and Greenland is geothermally related.
One of the theories which we heard from a glaciologist, which is a CO2 fan, that that geothermal flux was there forever, and it's not. Since it's been there forever, there is no proof saying that it's causing the melt of the Antarctica.
Antarctica is a very, very large place. What most people don't realize is Antarctica is about 1.5 times the size of the conterminous United States. It's a very, very large area. And the flux under there varies over time and over space, as with anything else. So at its greatest thickness, the Antarctic ice cap is over 2 miles thick. So most of the geothermal flux will affect the thinner parts of the ice cap. And it has led to, yes, glacial melt. There's some, we don't really know what the extent is. They're just beginning to map the geothermal sources under Antarctica right now.
We can see that ice is melting more and more. And basically, could we say that the geothermal flux is getting much more active these days? That's why it's causing, because it's not melting entire Antarctica, it's only melting one side of it, right?
Right, that's correct. Yes, the flux globally has increased tremendously since the early 90s. That is, the number of earthquakes and therefore the amount of geothermal flux globally has been increasing. As my charts show, the mid-ocean spreading zones are the nexus, or they're the point where this is occurring most. And yes, it has been increasing. As to what causes it to vary, it's still a great unknown. There's a lot we don't know.
Could you tell us the connection between geothermal flux and volcano eruptions? And do we see volcanoes on the rise, eruption on the rise? Do we have a data set proving it?
I would have to explore that a little more deeply, but we do know that earthquakes have been increasing. And again, we know that if you're looking at where the plates subduct, they are going to pull the plates apart in the middle. So this is what's happening, is that you have it's a push and pull system. Whereas where plates subduct, the plate is being pulled down into the mantle, but then it leaves a gap at the back end of the plate, and that's where more mantle material is able to ooze up and form new crust. So it is an interconnected system, yes. So the more plate dive that you have, meaning the more superficial volcanic eruptions you have, you should get more underwater volcanic eruptions as a result.
So basically, that's why we see the increase in Iceland activity, and because it's in the middle of the ocean.
Yes, in fact, it's part of the mid-ocean ridge system. Iceland is actually part of the Atlantic mid-ocean ridge that is happens to be above sea level. The rest of it's all below sea level. In fact, as you get off the coast of Iceland, it's called the Reykjanes Ridge. It's a series of underwater volcanoes that are all connected.
Mm-hmm. Wonderful. If you like, I would love to ask you if you would look into increasing amount of volcanoes. Is also, for some reason, when we talk to volcanologists, they all seem to be very into the volcano of their lives, and they don't look at the broader picture of them as a,
Mhm.
system as a whole, and they cannot. It's very hard to obtain data proving that volcanic activity is on the rise. And it sounds obvious when you talk about, since there's more activity at subduction zones, geothermal flux is getting more active, there should be more volcanic activity.
Actually, what I can directly glean off of my database is total seismic activity. I can vouch for that, that the total amount of seismic activity has greatly increased since 1995. That is clearly indicated in the data set, and I will send you that data if you'd like to see it. Since 1995, seismic activity globally has increased greatly, especially underwater seismic activity. There's still a lot that we have to learn about climate change. And I believe that I have found a small piece of that. That is, I believe that seismic activity, which has been largely ignored in the literature, is one of the drivers of that climate change, and we need to explore it more, and we need to better integrate it into other understandings that we have about climate change.
You mentioned about this shift which was occurring, and so you're talking about this this drastic shift of the core to the north, which occurred in 1997-98, and it was recorded by the shift of the Earth's center of the mass. And after that event, it was the Earth accelerated and centrifugal force changed, and the more destructive seismic activity started. You were referring to that event.
Yeah, there's one theory that's out there. In fact, Lord Christopher Monckton spoke about this at the COP26 conference. That there is a Earth's barycenter, as it's called, has shifted, and that barycenter shift has created a situation where there will be more earthquake activity because the plates will flex in response to greater gravitational forces being put upon them. The theory that's called plate flexure theory, they've also tied it in with El Niños. That is, as water sloshes around in the Pacific, it puts more pressure on plates, and it can actually cause more volcanic eruptions at the back end of the plate. It's pretty complicated stuff, and as I said, we haven't worked out the details on this yet. And as I said, there's a lot more work to do in this area.
Thank you very much. And we also would like to ask you about this, that a few decades ago that oceanologists were recorded hot blobs in the ocean, and it is 5 to 10 degrees above the host water. It was found on the coast of Antarctica, on the coast of Alaska, and other places. So where water is not expected to be so hot. And so could you share a bit your opinion on this phenomena?
That is an excellent question, one that I would like to do more research on myself, for these hot blobs. I believe what is happening is that in addition to changing the thermohaline circulation, if the seismic activity and the geothermal heat release is close enough to the surface, I believe that through convection, that is the heat simply rising up, I believe that can cause this to also warm up, and you will get these hot blobs or streaks that we see in the ocean. We see one off the coast, east coast of North America. We know that there is a geothermal seep off the east coast, and that's giving us a tongue of warmer temperatures creeping up the east coast. This is unexplored territory. As I said, James Camus has done some work on this, but we're just now beginning to take a look at this. Unfortunately, I don't have any funding or research assistance to do this, but there are many, many unanswered questions. This is one of the things on my agenda to look at down the line. These mysterious blobs. Off Antarctica, there seems to be more and more evidence that this is geothermally driven. Off the Aleutian Islands, we know that we also have what are called, we have very complex convergence zones, and these areas are called back arc basins. So that as one plate dives under another one, it actually splits small pieces of the plate right behind that. And that gives you extra geothermal release close to the surface. That may in fact be what's going on here. But this is This is terra incognita at this point. We still don't understand that. The problem is that most of these researchers won't look at it because it doesn't fit the paradigm of, well, CO2 must be causing all these hot blobs, it must be causing the melting of the ice, et cetera, et cetera. So what happens is they tend to get very myopic in their view as to how they approach this. We will see that we also have a lot of back arc basins all around that Pacific Rim of fire. I specifically excluded the back arc basins from my analysis because there it gets very, very complicated, because sometimes you can record large amounts of seismic activity, but you don't have a lot of activity in the back arc basins. And that you have to start reading those out literally basin by basin. And this is where we need much, much more detailed data and many, many more detailed studies in order to sort of pin that down. And this is, again, this is a pretty, it's a budding branch of research that I think needs to get a lot more attention, and it just hasn't. And this is where organizations like NOAA, the U.S. Geological Survey, they need to start getting some funding, putting that together, and getting it out there to try to get some answers to some of these things.
As far as funding goes and researching, we don't have no funding, but we have an army of people who are willing to assist and do the footwork and help you with research. I know there is a lot to do when documents, and we have proven that we are capable of collecting the data and putting ends together. So if you need help in that regard, we are very willing to do that.
Thank you. I appreciate that. And as an initial offering on all this, as I said, I will be happy to send you all of my data. You can have every bit of it, all the spreadsheets. There's 42 years worth of data with this. I can aggregate it, disaggregate it. I can do some of the analysis for you. But then at some point, I think it'd be great if some of you folks could sit down and ask your own questions and start to work with that data directly. And I, of course, will show you how to extract that data. It's not a very hard thing to do at all. It's a relatively simple spreadsheet exercise. That's because the IRIS database is a very sophisticated database, and they've pretty much worked out, I think, all the details that need to be worked out on this. It's a pretty remarkable database. It's probably the most remarkable database I've ever seen out on the internet. It's phenomenal, and it is open access. But I think that would be a good starting point for us, is to have a data sharing, and then to start to pose questions to that data that we can then collectively sit down and start to answer. I think that's a wonderful idea.
Yeah, thank you. It's really amazing offer, and we are happy really to have your scientific support, and of course data. I think world most precious thing nowadays is data. So
yes,
when you have data, then you can rule the world.
Absolutely. It's all public access information. As I said, I've cataloged it and siloed it and put it into different bins, and I'll be happy to send it. And as I said, it's a good starting point for all of us.
When I look at your map, when you were showing where we have hotspots, and we for sure had these hotspots in the ocean at the north, close to Greenland, and which you show in the ocean. We were reading this most recent articles on Gulf Stream. I know that you already answered that question, but essentially, we also found information that it was time in the past and Gulf Stream was stopping. And, just as one of the hypotheses we have, that what if the heating, is it possible that heating from the bottom become so strong that this gradient of the densities does not work anymore at this particular part, which is referring to Gulf Stream? I'm not telling about the overall circulation stop, but only the part for Gulf Stream. How possible this scenario? What is your opinion on that?
Wow, yeah, that covers a lot of ground. There is a theory out there called snowball Earth, that they believe at times in the geologic past that Earth was completely covered by ice. And that what happened was that we built up so much geothermal heat at the bottom that it served as a capacitor, as a the ocean served as a giant heat store. And it was able to then erupt through the ice, start to break the ice up, and get the currents flowing again. Because effectively, the vast majority of water that's moved by currents, of course, it's wind driven, but it's also driven at the bottom. They call it tunneling. So so they talk about bridging effects in the ocean, that is atmospheric effects that move water, and then tunneling, that is the things that are moving the water underneath the surface. So as to whether or not it serves as a capacitor, there's a lot of evidence that it does serve as a large capacitor. Now, a major theory right now, and this all fits in with the CO2 idea, is that if we continue to melt snow and ice at the rates that we have, it's going to freshen the waters in the Arctic. When you freshen the waters of the Arctic, it slows down the thermohaline circulation. And because what it does is it ices things up, and the thermohaline circulation will shut down. So this is how they've justified their argument that the Gulf Stream is slowing down. Well, it must be slowing down because we've melted so much snow and ice, and we have much more fresh water in there. So the thermohaline circulation must be slowing down because our models say it should be slowing down. Unfortunately, as I said, there's one article by Josh Willis that came out in 2011 showed that the Argo data showed that no, it's intensifying, and I'll show you that. So you have observational studies versus modeling studies, and they don't seem to match up. If they keep pursuing the CO2 hypothesis, that is one molecule in 10,000 is running the whole show, they're going to keep ending up with, I think, bad models that are going to give them bad results and lead them to bad conclusions. Unfortunately, it's all been highly politicized too. There's power and money involved in this as to who's controlling energy sources and how energy gets transported, and what are the sources and the sinks for all this energy. So I think that there's a lot of political clout and a lot of money involved in all this that has just overwhelmed the science. So I think we have a modeling problem as opposed to an observational problem. And we still don't have, as far as I'm concerned, good data on any of this. But I think this capacitor idea is very, very interesting. In fact, just to show you how this thing all flips around to meet certain agendas. There's a famous researcher who I shall not name, who actually came up with the term AMO, Atlantic Multi-Decadal Oscillator, 20 years ago. He just came out with an article 3 months that says it doesn't exist anymore. It's no longer a viable concept. And meanwhile, there are hundreds of articles written that document its existence, that have documented these western boundary effects of warmer waters coming up on the western shores, such as in Greenland. It comes up from the western part of the current. Part of the current does wrap around Greenland and comes and curls back around south. So those current studies are critical. There have been very few of them done. We simply, again, don't have enough information about it. But if we keep trying to pigeonhole all of this into this carbon dioxide box, I think we're going to keep ending up with these sorts of problems, and we're going to be barking up the wrong tree, so to speak.
Thank you. Thank you very much. We have one question from Lisa. Lisa, will you be able to share your screen?
We're trying to make the graph for ourselves, which is represent earthquakes by the depth and the amount of them. So we see that not only magnitude is rising, but also the dipping. It goes extremely deeper, yes, and here is a number of earthquakes deeper under the 700. So
we found there are quite a few earthquakes at the 700-kilometer depth, and they only increase lately. We see a lot of them. Anything about that you would like to share?
That's interesting. So the deeper earthquakes are, because interestingly, at the mid-ocean spreading zones, those are all shallow earthquakes. Most of those are within 10 kilometers of the surface. So
these ones are on the Great Pacific Ring of Fire, and they usually go along the coast of Japan, Philippines, and so on, along that coast.
Can I make a comment here as to the data that you have? You're looking at magnitudes above 3.
Yes, yes,
And
absolutely.
I got into an argument with a seismologist at Harvard over this. I specifically looked at magnitudes of 4 and higher, because those are the ones that the global seismic network can get.
Okay.
Once you go below 4, you start to have serious sampling problems. And by the time you get down to 3, you're only going to pick up, you're going to have seismographs relatively close to the area. So in many respects, you could be looking at the artifacts of the number of seismographs that you have and not the true number of earthquakes, but I'd have to look at that more.
Okay.
So that's another consideration that has to be made. That's why I picked 4 and higher.
No, that's a good point. But the great depth ones, they're usually 6 and higher. They're not even 4. They're 6, 7,
That's
8.
correct. That's correct. And it would be interesting to then break them out by magnitude. So those charts would be very, very interesting. You're right. The deeper the earthquake. That's why most of mine are shallow earthquakes, as I said, 10 and less. So that would be another way to start to analyze and to dissect the data. Well, my data contains all of that. It contains the entire global data set from 4 to 6.
Okay, because well, first of all, they seemed to be extremely rare, those 500, 600 depth, kilometer depth earthquake. And now we have, and they, like once a year they used to be, and so on. And sometimes they were considered a fluke of nature. But now we see like 1 a week, and the depths are growing. They're going 600, 700, 750 kilometers. And the magnitude is rising as well at that depth.
That's interesting. As I said, that's a part of the data set that's new to me. I haven't explored that part of the data set, but I think that'd be fertile ground to start doing some work on. But we know the climate data has been heavily altered and modified. And one of the things I would like to do is to be able to take what's called the Palmer Drought Index data and sort of reanalyze it, sort of re-engineer it, because that has temperature data embedded in with it. And I know that I haven't tampered with that, because the Palmer Drought Index goes all the way back to 1900. And from that, I think you get a better read on what the actual surface temperatures have been for the US and for the globe, because they do have it for different parts of the globe. The data tampering problem is very serious stuff. And what that does is it corrupts the scientific process to the point where it now becomes advocacy and such.
Yeah, and the most importantly, it may put people to the danger. I mean, if we are at the rise of the seismic activity, I think a lot of people really hope that they will get this information, and it would corresponding adjustments should be done so that to prevent any possible major earthquakes.
Yes. Oh, absolutely. I mean, one of my goals with this research is I've noticed that the last 2 largest El Niños on record, the one of 1997, 98, and the one in 2016, were all preceded by large jumps in mid-ocean seismic activity. It's a 2-year lag. It's a 24-month lag. So if I start to see that seismic activity jump up again, I will then make a prediction of a large, record-breaking El Nino, and hopefully fishing, agricultural, settlement, hydrologic communities can adjust to that sort of thing. And there's a lot of value to be able to predict that sort of stuff. But you're right. This is the sort of thing that we can't lie about these things. We have to be totally objective the entire time.
There was a common knowledge known that any volcanic eruption is actually causing more, like throwing out more CO2 than entire humanity in 2 years. But lately, somehow they managed to show the data saying that humans are throwing out more CO2. And
Yes.
where do they get how do they calculate how much CO2 we throw out? Where do they take the data?
They pretty much look at how much fossil fuel has been burned. They will look at the total CO2 content, and then they'll look at how much fossil fuels burned, how much petroleum is used, natural gas, coal, and from that they are able to estimate how much CO2 is going to be a product of all of that, assuming it's going to have a residence time of 10 years or more. And that's how they get the estimate that humans have been contributing more. Also, but yes, nobody has sat down and tried to estimate how much CO2 is coming out of the mid-ocean spreading zones. We have no idea. Also, too, as the oceans warm, it emits CO2. CO2 comes out of solution, and that also ends up in the atmosphere. And I don't think anybody's accurately calculated that. So again, another excellent question, and one that I think remains unanswered to this day. Again, I think a lot of it's politically driven, to be honest with you. I really do.
Yeah, thank you very much. And just I would like to switch to our last question we ask every scientist, and like Creative Society project, what we emphasize, as I already said, that human life, like just that we promote the idea that human life should be the highest value for society. And in this situation, we kind of have person in the center of everything, and every process which is occurring, they kind of, they help to serve people, and so that their talents could be flourished, that we would not have cases with hunger or something like that. And like our current format we call consumeristic society, because essentially we are raised as a consumers from very early age, and that we need to consume more, to buy better things, and to kind of and we treat each other in the relationship as we have this transactional relationship, like you give me, I will give you. And like my question is essentially, how do you think how it is important for people on the planet to unite now and to change the format of society from a consumer society to the creative one, where the value of human life is on the first place?
I believe that we should be good stewards of the earth, and we should use the resources that we need, and that we should try to preserve resources as best that we can. But yes, humans do come first in the equation. And yes, in an ideal, perfect world, everybody would have access to food, to water, to shelter, to healthcare. And sure, all of those needs should be met first. I agree. I believe that the earth is here for our use, and we are not to just sit there and fret about frivolous things concerning our planet, like did a single plastic straw kill a turtle? These seem to be sort of the frivolous causes that a lot of folks are getting involved in. And I used to give an example. Let me, by way of example, sort of express how I feel about this. I used to talk about the spotted owl here in the United States, well, the Pacific Northwest. The spotted owl, of course, was endangered because they were taking down forests in Washington, and I believe in British Columbia also. And a lot of the environmentalists got on board and said, wait a minute, you're destroying the homes for these spotted owls. And my comment was, well, you have a choice. Either make homes for the spotted owls or make homes for humans, because the lumber is being used to build homes for humans. And yes, I believe in humans first, and I believe that we should exercise good stewardship, but that we should all try to take care of each other and make sure that, yes, I don't like disparities in wealth and all of the inequality that we see. But at the same time, I think creativity and hard work should also be rewarded at some point. So I've got sort of a mixed outlook on that. But yeah, humans definitely first. I'm all human. Thank you so much. It's been a real pleasure meeting with you, and I look forward to doing some work in the future. I think there's a lot of potential here.
Thank you very
Yeah.
much.
Thank you so much. Thank you, Professor. Yeah, thank you for your time.
Thank you.